So linear approximation. Linear approximation is an important topic in AP Calculus, but in order to understand what linear approximation is, you need to understand where it came from and why we have it. So first of all, why we use linear approximation is take, for example, a function such as y equals square root of x. We all know that y equals square root of 16 is 4. Because that's a perfect square. But what happens when we get one that's not a perfect square? What if we are asked to evaluate y equals square root of 16.1? And of course your first initial answer is, well, I'll just put it in my calculator. But the question behind that is, well, how does the calculator know what to do? Because the calculator is just estimating, and some human being had to come along and program that calculator to do that. And what about before they had calculators? They still were able to get a good idea or estimate of what this square root was. So that's where linear approximation comes into play. That's why we have it, to evaluate functions that aren't so easy to evaluate mentally off the top of our head. So if I zoom infinitely close to a point on a curve, so for example the square root of x, no matter what the function, it will be locally linear. What that means is if I zoom in infinitely close to that point, x equals 16.1 on that curve, it'll start to look like a straight line. In fact, it'll start to resemble the tangent line at an x value that is easily evaluated. In other words, if we have the graph of the square root of x, and let's say this is x equals 16, so this is where y equals 4, and at 16.1, so that would be approximately here. Here's the tangent line for x equals 16. And if I zoom in really close to this section of the curve, it's going to start flattening out and becoming a straight line. And the section of the curve at x equals 16.1 is going to start looking like that tangent line. So the idea is that if a function is a little difficult to evaluate, but the equation of the tangent line is not, and it's not because it's y equals mx plus b, that's easy to evaluate without a calculator, then I can use the tangent line equation to get a good estimate. So I use the tangent line equation of a point nearby to evaluate, or not evaluate, but estimate the value of the function at a more difficult x value. So how do I complete this process? I mean, how do I estimate using the tangent line equation? So it all goes back to some basic algebra 1, where when we're finding the equation of the tangent line, we use the equation of a line, which is y minus y1 equals m times x minus x1. Well, when you get into high school, you got to make it look a little more sophisticated. So we are going to start using function notation. So instead of y1, we're going to write the function evaluated at some c value. That's function notation. And then m times x minus x1, well, the x1 would be the c value, so minus c. So now I'm using function notation, exact same equation of a line format, but it looks a little bit more complex. Even though it's not, it means the same thing. And then when we throw calculus in there, so using calculus to rewrite the same formula we worked with repeatedly, I'm still going to use function notation, but instead of writing m, I'm going to write it as the derivative evaluated at that x value, because that's really what it is. That's the slope, and the slope at the c value is just the derivative. So that's where the tangent line equation comes in. Now what you're going to see in your textbooks and things like that is local linearization is a formula. All they did was they took this minus f of c and moved it over here. So local linearization, they tell you it's a formula, but it's not. It's just the same linearization. Okay. It's the same formula you've been working with, it just looks different. If I add f of c to both sides, it looks like this. Y equals f of c plus f prime of c times x minus c. Same thing as over here, they just move the f of c here by adding it to both sides. And this is the formula that they tell you you have to memorize, but you don't have to memorize it because you know it already. It's just written using calculus. Alright, so this is all well and good, but how do we apply it to our original situation where we had y equals the square root of 16.1? Well, you choose an x value that's easy to evaluate. So obviously our x value is going to be 16. So we're going to use the c value of 16. It's a value that's close to the one that they've given me. And when I zoom in really close, that tangent line will be close enough at c equals 16 to get a good estimate. So first we need to figure out what our function is, and it would be f of x equals the square root of x. That's our main function here. And then we'll need the derivative, so the derivative of that is 1/2 times x to the negative 1/2. And then we'll move on to our formula. So our formula for linear approximation is y equals f of c plus f prime of c times x minus c. And once I plug in all the information I have, f of c would be the square root of 16, our c value. So that would be 4. F prime of c, well, f prime of x is 1/2 x to the negative 1/2. So f prime of c would be 1/2 times 16 to the negative 1/2, and then times x minus c, which is 16. And so the square root of 16 is 4, and it's negative, so it's going to go on the bottom. So this would simplify to plus 1/8. And then this would be our equation that we use to approximate what the square root of 16.1 is. So what we do is we backtrack to what we were originally trying to find. X would equal 16.1, so I plug that into my tangent line equation. So I get y equals 4 plus 1/8 times 16.1 minus 16. And then this would simplify to 0.1. And then from there, we're trying to evaluate without a calculator. So I'm going to divide 0.1 by 8, the old school way. So this would give me 20, and then 2, 16, 4, and that would be 40, so that would be 5. So my section here would simplify to just 0.0125. Therefore, when I add 4 to it, y would equal 4.0125. So that's our approximated value for the square root of 16.1. We're saying it's approximately 4.0125. And let's test to see how close we were. So if we actually test it in a calculator, which is basically using the same method as us, it's just a little bit more accurate. Let's see, 16.1 square root would be 4.0124. And if you round it up, it's exactly the same as our estimation. So it works really, really well. First thing, you pick a C value that's close by. So that's when we chose C equals 16. So close to the given X value. Next, you find your tangent line equation at that C value. And that was where that formula, but it's not really a formula because you already know it, you've been working with it forever. Y equals f of c minus f prime of c times x minus c. And then you evaluate the tangent line equation at the x value. So once you get all your c's filled in and you've simplified, then you plug in the x value for x and you get your estimate. And that is linear approximation.